myself Lokesh Soni and working as an assistant professor in the Akgec ECE Ghaziabad. So this is the second lecture in the continuation of number systems. So our next topic is how we can convert the hexadecimal and binary. As I discussed earlier, we have to take the pair of the 4 bits to convert the hexadecimal into binary. So we were taking the 4 bits in the last lecture, and we convert the binary number into a hexadecimal number. So in continuation on that, our next topic is the hexadecimal and octal conversion. How we can convert the octal number into a hexadecimal. So first we use a binary number system as an intermediate. That means first we have to convert the octal into a binary. So we have to take the 3 bits. We have to represent each bit in the octal into a 3-bit number. Like 1 we can represent 001, 5 we can represent 101, 6 we can represent 110. So the binary conversion of the octal number is 001, 101, 110. So this is our binary representation. Now we have to convert this binary number into a hexadecimal number. So for that we have to take the pair of 4 bits. Like these are the 4 bits. There is a decimal digit here. There is a decimal point after the 5. So this is a 5, so there is a decimal point. So if we have before decimal, we have to move from right to left. So we take the 4-bit pair here. There are only 2 bits left. So we will append the 00. Similarly, after the decimal, we will move from left to right. So here is only 3 bits. So we can now append 1 extra bit, that is 0. So if we can take the pair of 4 bits, this represents the 0. This will represent the 13. But in hexadecimal, 13 is represented by the D. And 1100 is nothing but 12. And hexadecimal, 12 is represented by the C. So our hexadecimal number is 0D.C. So that's how we can convert the octal number into a hexadecimal number. Next is the how we can convert the hexadecimal into octal. We can use the same procedure, like we can use the binary as an intermediate. So we will first convert the hexadecimal into binary. So in binary, 1 is represented by 0001. Since this is a hexadecimal number, so we have to take the pair of the 4 bits. 4 is represented by the 0100. C is 12 in the hexadecimal, so we can represent the 1100. So altogether this will represent our binary number. So from binary we now take the pair of 2 bits, pair of 3 bits for the octal, because octal is represented by 3 bits. So we can take the pair of the 3 bits now. These 3 bits can be grouped together, these 3 bits, and here 2 bits are left, so we can append 10 here. Similarly, after the fractional part, we can combine these 3 bits, only 1 0 is left, so we can append 2 zeros here. So the pair of these 3 bits are represented 0, this is represented 010 is represented 2, 100 is represented by 4, and 110 is represented by 6. So this is our final hexadecimal to octal conversion, which is 024.6, or we can neglect this 0. 24.6 is our final result for the hexadecimal to octal conversion. Next topic is fractions. Means how we can convert the fractional part, means how we can convert decimal number into another system. For example, if we are having a decimal number in the form of d dot d, where since it is a decimal number, so base is represented by 10. So for the integer part, that is capital D, for the integer part we have to divide the integer part by the base of the number in which we want to convert it. And for the fractional part like small d, we have to multiply the number by the base of the system in which we want to convert that number. For example, this is our decimal number and we want to convert decimal into a binary. So how we can proceed? As we can observe that the capital D is represented by 23, that is the integer number, and 0.75, that is the fractional number represented by small d. So as I mentioned in the steps, like for the integer part we have to divide the number by the base. So we have to divide the 23 by the base is 2, and in division we have to note down the remainder. Means after the division, what are the remainder will be there, we have to note it down from top to from bottom to top, like we have to note it down the remainders from bottom to top. If we divide 23 by 2, we get 11 here and remainder is 1. Again, if we divide 11 by 2, we get 5 is here, 1 is remainder, 2 is here, 1 is remainder, 1 is here, remainder is 0, and we divide 2 by 1, then remainder is 1. So we have to note it down the remainder from reverse order. So the result for the division is 1, 0, 1, 1, 1. This is the result for the integer part only. For the fractional part, we have to multiply the fraction by the base, and here the base is 2. And for the multiplication, we have to collect the integer part, like we have to collect the integer part of the multiplication results in the same order, like from top to bottom. In division, we take from bottom to top, but in multiplication, we have to take from top to bottom. So if I multiply the 0.75 by the base, here base is 2, we get 1.5, and we have to note it down the integer part. Integer part is 1 here. So 1 is noted down, left is 0.5, 0.5 multiplied by 2, we get 1.0, note down the integer part, we are left with 0.0 only. So the result is 0, we are not getting any integer part. So we have to stop it here, and so the final result is, if we move from top to down, is 1, 1. So for multiplication, the result is 1, 1. So if we can combine these two, we are getting the decimal to binary conversion is 10111.11. That's how we can convert the decimal number into a binary. For the second example, how we can convert the decimal into octal. Again, we have to find out the integer part and the fractional part. Here integer part is 23. So we have to divide 23 by the base of the system in which we want to convert. So here the base of the system is 8. So we have to divide it by 8 and note it down the remainders. So if we divide 23 by 8, we get 2 and remainder is 7. Again, if we divide 2 by 8, we are getting here 0 and 2 is here. So, and for division, we have to move from bottom to top. So, the result for the division is 27. For the fractional part, we have to multiply the fractional part by the base of the system, which is 8. If we multiply this, we get 6.00, and we have to note it down the integer part, which is 6. So we left with the 0, 0. So we have to stop it here because we get the 0 at the answer, and we have to note it down from top to bottom. So the final result for this conversion is 27.6 from decimal to octal. For decimal to hexadecimal, again we have to note it down the integer part and fractional part. So first divide the integer part by the base of the system. Base of the system is 16. So we divided by 16, we get 1 here, 7 is the remainder. Again 16 is not divided by 1, so 1 is here and 1 is here. And for division we have to move from bottom to top. So the result for the division is 1, 7. For the fractional part, this is 0.25. So for the fractional part, we have to multiply by the base of the system. So we multiplied 0.25 by 16, we get 4.00. So the integer part is 4. We have to note it down, and the remaining is 0.0. Multiply by 16, we get 0. So we just have only one integer part. We have to note it down from top to bottom. So the final result for the conversion is 17.4 from decimal to hexadecimal. So that's how we can convert any decimal number into any other base by just division and multiplication. Coming to your next topics. First, the topic is weighted and non-weighted binary codes, followed by the BCD codes, access 3 codes, gray code, and Hamming code for error detection and correction. So first of all, what is weighted codes? Weighted codes, the definition says that each position of a number represents a specific weight. The bits are multiplied by the weights indicated, and the sum of these weights will give the equivalent decimal digits. As we can perform many examples on it, like as I use for the 4-bit number, the weights are 8421, which is represented by the 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. So the weights represented by the equivalent binary numbers, we have to add them and we can get the binary numbers, decimal equivalent of that number. For the non-weighted codes, means there are certain codes which are non-weighted, means the codes which can't be represented by the 8421 or 421 weights. These are the access 3 codes and gray codes, which I will explain in the upcoming slides. First is binary coded decimal, that is BCD. What it is? A decimal number can be directly represented by the BCD code. BCD number is valid from 0 to 9 only. After the 10 to 15, 10 to 15 is the invalid BCD numbers. So the conversion of the decimal digit into a BCD is very simple. Just we need to represent each decimal digit by their equivalent 4-bit binary number. Like for 185, 1 represented by 4 bits like 0001, this is 1, 8 is represented by 1000, and 5 is represented by 0101. Just we have to represent each decimal digit by its equivalent 4-bit binary number. For example, if we want to convert 1 to 5.8, 1 to 5.8 into a BCD, just we need to replace it by 4-bit binary equivalent like 0001, 2 is represented by 0010, 5 is represented by 0101, and 8 is represented by 1000. So this is our equivalent BCD number. You can observe here from this table, 0 is represented by 4-bit BCD like 000. Same 4 is represented by 0100 if we are using the 4 bits binary weighted code 8421. 6 is represented by 0110. Similarly, 9 is represented by 1001. Since this table represents only from 0 to 9, as the BCD numbers are valid up to 9 only. If we are given some BCD number, how we can convert into a decimal? Just in the previous slide, you can observe that if we want to convert any decimal into BCD, we have to take the we have to represent that number into a 4 bits. Similarly here, if we are having a BCD number, we have to just pair the 4 bits. And the equivalent of the decimal of these bits are final result, like 0111 represented by 7, 0110 represented by 6, 101 represented by 9, 0101 represented by 5, and 0100 represented by 4. So this is our equivalent decimal representation of the BCD. As I mentioned earlier, the invalid BCD range is from 10 to 15, 1010 to 1111. So if any number is given in this range, this is an invalid BCD. We can't represent it by simply 4-bit binary equivalent. Next is access 3 code. What it is? Access 3 can also be obtained from the BCD number. We have to just simply add to each decimal digit, or if we can represent a binary equivalent, we just add 0011, because binary representation of 3 is 0011 if we are using the 8421 weighted code. So there are two ways to represent the decimal into access 3. One way is that if we are giving a number 53 and we have to convert into a access 3. So one method is that this is a decimal, so we can simply add 3 to it, we get 8. We have to just simply add 3 to each digits of the decimal number. This is a 3. This is 3, 3 plus 3 is 6. So one way is that the each in decimal representation, if we are giving some number into a decimal form, we have to just simply add 3 to it, because this is a access 3 code, means we have to add 3 to each digit in a number. So finally we get 86, and this is our access 3, so we have to just convert into a BCD form. 8 is represented by 1000, 6 is represented by 0110. So this is our final answer in the access 3 in the form of BCD. Second method is that if we, this is the first method, we can add the 3 to the decimal digits. In the second way, we can first convert the decimal into a BCD, like 5 BCD representation is 0101, 3 BCD representation is 0011. So for access 3 we have to add 3 into it, so we can add 30011, and here we can add 30011. The result will be same. So we can add 0101 to 0011, we get 0, 0, 0 and 1, which is equivalent to 8, which are getting here. Same here, we are getting the 0110, which is equivalent to 6. So you can choose any method, final answer will be remain same. So the range of the access 3 code is from 3 to 12, because if we are having a BCD number of 0000, in access 3 it will become the 3, because in access 3 we have to add 3 into each BCD number. So it will become 0011. That means access 3 code will start from 3, not from 0. And again, if we are having a 9, because BCD is valid up to 9 only, 1001, if we add 3 into it, plus 3 plus 0011 plus 0011, we get 12. So the BCD range is from 3 to 12 only, because 012 will not appear in the access 3 code, because it will start from 3 and it will last up to 12, because BCD is valid up to 9, and 9 plus 3 will become 12. So the invalid access 3 numbers are 0, 1, 2 and 13, 14, 15. These are invalid access 3 numbers. As you can observe from this table, if we are having this number, this is equivalent to 1, and 1 plus 3 we are getting the 4 here. This is equivalent to 2, so 2 plus 3 we are getting 5 here. If we are having any number, this is equivalent to 6, and 6 plus 3 we are having a 9 here. Similarly, if we are having this number, this is equivalent to 8 in BCD. So in axis 3 it will become 11. So this is 11 in the axis 3. So that's how we can convert any BCD number into a axis 3, just by simply add 3 into it. Next is the gray code. It is a binary code in which only one bit change is allowed between the two successive gray numbers. Like in a binary numbers, we can observe that in binary numbers there may be a like we have 0, 0, 0 and last number is 1, 1, 1 in 3-bit representation. So we can observe that in binary all 3 bits will be changed. But in gray code this is not the case. In gray code there is only one bit is changed at a time. There will be a not more than one bit will change. So this is the advantage of the gray code. If we are talking about the practical applications, so gray code will be used because here only one bit is changing at a time. So it will consume less energy and less power. Gray codes are also known as cyclic codes. For the gray code, first we need to understand the XOR gate. What is XOR? This is the symbol of XOR gate, where there is a two inputs A and B, one output Y. So the truth table of the XOR gate is having a 2 inputs A, B. So 2 bits having a 4, equivalent 0, 0, 0, 1, 1, 0, 1, 1. So in XOR gate for the same bits, the output will be 0. A and B are same, their output will be 0, and for the opposite case, the output will be 1. So this is the representation of the XOR gate truth table. The first is binary to gray conversion. How we can convert the binary code into a gray code? So the first the MSB will be the same, like the binary number is 1, 1, 0, 0, 1, 0, 1 is given. So how we can convert this binary into a gray? So MSB of both is same, means MSB bit should be same. This is a binary number and this is a gray representation. So MSB bit should be same. To obtain the next bit in the gray code, XOR the conjugative binary bits. That means we have to XOR the conjugative binary bits, like 1 XOR 1, same bits XOR is 0. Again 1 XOR 0, these are opposite, so output will be 1. 0 XOR 0, since these are same, so output will be 0. 0 XOR 1, the bits are opposite, so output will be 1. 1 XOR 0, output the bits are opposite, so output will be 1. And 0 XOR 1, the bits are different, so output of the XOR gate is 1. So this is our gray representation of the given binary bit. So that's how we can convert any binary bits into a gray code. Thank you everyone for listening this. We can continue after this.